Alright, so coming back in, we're now playing around with the graphical interpretation. I'm going to give you some information in a graph, and your job is to be able to answer questions. And like I said in the previous video, what we're going to do is we're going to use the graph, and I'm going to do part I, and I'm going to leave part 2 II, or part 2 for you to do. Now here are all the questions. Now a couple of things to notice and what you have to be very, very careful of on the AP, which is which graph did they give me. So the first thing that we want to notice here is that this is the graph of f prime of x. So I'm just going to make this darker to emphasize that this is the graph of the derivative. So we want to make sure that we don't get confused, because you want to make conclusions based on the fact that this graph is giving us information about the derivative. Okay, so let's come up here to A, and in A it's asking the question. All right, first of all, let's read the given because that's always important. We have the derivatives given of two continuous functions. So the function f is continuous. So f is continuous for the picture that we have here, which is 0 to 9. And obviously, by looking at my derivative, since there's a point everywhere from 0 to 9, we could say that f is differentiable 0 to 9. Okay, it actually probably was differentiable for 9 and 0 as well, because there's a point there, but it's kind of a gray area. We'll just say it's differentiable on this open interval. So we definitely know that. Now, in part A, it's saying what open intervals is f increasing or decreasing. Now relate this to the graph you were given. F increases when your derivative is greater than 0. It decreases when your derivative is less than 0. And since I'm looking at the derivative graph, I'm going to add even more detail to that, which is when f prime is above the x-axis and this would be f prime below the x-axis. So that's giving me what I'm looking for on the graph. So once I do that, now I'm going to come down and I can use, let me move this to this side, that I can use the graph to answer the question. And I can see that I am above the axis from starting here at 1 and going over to 6. Okay, so we would say f increases for 1 to 6, and then it also increases from 8 to 9. And our reasoning would be because f prime of x is greater than 0. Then we would say that f decreases for, where is it below the axis, from 0 to 1, and from 6 to 8. And that's because your derivative graph you were given is less than 0. Okay? And when you're given a graph, make sure that your justification uses the graph as your reason. Okay? Because that's what you were given. Alright, now let's take a look at B. And what B is asking is, on what intervals is f prime of x greater than 0 and f prime of x less than 0? Well, hopefully you recognize that this is exactly the same reasoning as above, so I'm going to say CA. Same answer. All right. Now I want to know, at what values of x does f have a local max or a local min, relative extrema? All right, so now let's think about what we want to have. We want to have, what we learned is that we needed to have a critical value. Okay, so this occurs when f prime of x is equal to 0. And what does that mean on the graph? That means an x-intercept of f prime, or it does not exist, but we don't have that case here. All right. And, Okay, that's not enough. Just because f prime equals 0 is not enough. And f prime has to switch signs, which on the graph, what that basically means is you need to cross the x-axis, that you can't go up and bounce and come back down. Okay, that you actually have to cross the x-axis. So let's answer our question. So now we figured out what we're doing. I'll put this in blue. If I look over here, the x-intercepts are at 1, 6, and 8 for f prime. So that is this part. And then I ask myself the question, does it switch signs? Does it cross the x-axis? Yes, yes, and yes. And then I might ask myself, which way is it crossing? Because remember, it's the plus to minus that's telling us whether it's a relative max or a relative min. Here, your f prime is negative to positive. So that's a relative min. This one goes positive to negative, so that's a relative max, and this goes negative to positive, so that's a relative min. So our answer to C is going to be that at x equal to 1 and 8, there is a relative min because f prime switches from negative to positive, and of course f prime of 1 equal to f prime of 8 equals 0. And then also at x equal to 6, there is a relative max because f prime switched from positive to negative, and f prime of 6 was equal to 0. All right, so interpreting our graph. Now we're looking at on what intervals is f concave up or concave down. So I'm going to write my what's going on over here. Now remember, f is concave up or concave down when the second derivative is positive, concave up, or second derivative is negative. Let me just leave a little room in here. But we don't have a graph of the second derivative. We have a graph of the derivative. What does that mean about the graph? What are we looking for on the graph? We are looking on the graph for, the second derivative is concave, or second derivative is positive when the first derivative is increasing. And here it would be when your first derivative is decreasing. All right? And then if those two things are true, then we know f is concave up here and concave down there. So I'm looking for concave up. I'm looking for where the derivative graph I was given is increasing. For what values? All right. So I'm going to start writing my answer down here for that one. What letter are we on? We are on D. Okay. So f is concave up for the same values for which f prime is increasing. So it increases from 0 to 2. It increases from 3 to 5. And it increases from 7 to 9. And so our reasoning would be because f prime is increasing on these intervals, which means the second derivative is greater than 0. All right? F is concave down for places where f prime is decreasing, so 2 to 3, and 5 to 7. And those are the only two intervals of decrease, and that would be because f prime is decreasing on these intervals, which means your second derivative is negative. All right, let's look at E. We want to state the x-coordinates of the points of inflection. So now remember that points of inflection occur where F changes concavity. That has a point that is not a cusp. Then we have what's happening on F prime. F prime would have to switch from increasing to decreasing, and your second derivative would have to switch signs. So since we don't have our second derivative switching signs, we don't have a picture of the second derivative, we know that what we're going to do is we're going to look at the graph and we're going to look at where the derivative switches increasing, decreasing, or vice versa. It doesn't matter in this case. Okay? And we want to make sure that F prime existed. Okay? We want to make sure that F prime existed and that there was no cusp if F prime does not exist. I'm putting a star by this one because I'm going to point over here to the one that you're going to do on your own. But in this problem, we knew that F was continuous, and I know that F was differentiable because it existed everywhere in this example. So I don't have to worry about the cusp versus vertical tangent line or discontinuities. So all I'm looking for is where F switches concavity, where F prime switches increasing and decreasing. So the answer to E would be there are points of inflection at x equal to, and when you're basically looking at where you switch increasing and decreasing, what are you looking for? You're looking for relative extrema on F prime. So I have a relative extrema here, 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 and here. And so there are 4 points of inflection on F. So at x equal to 2, 3, 5, and 7, because F prime switches from positive to, or let's just not say from, because it doesn't matter which way it switches. Let's say switches signs. So my second, oh no, it doesn't switch signs. I see that's where you start getting confused because you've got 3 of these things. Switches direction, let's do that, slash increase, decrease. So F double prime switches signs. All right. Now let's look at the next part, which is F. We're going to assume that F of 0 equals 0 and sketch the graph of F. All right, so F of 0 equals 0. Let's pick, I'm going to do pink here. So F of 0 equals 0. Now, this is a preview of coming attractions. Okay? Remember that you kind of, if you know the rate of change, shouldn't you be able to take a known value and then figure out how much the change is in between each value? Like if I know what the actual rate of change is. So kind of looking at this, remember that we did some problems. I'm trying to remember if I did it this year or not. All right, well, I'm just going to assume that I did not do them this year, just kind of re-explain it. That if I were to calculate this area in between the curve and the x-axis, okay, so let me pick a different color than the one I'm using for my graph, say yellow. So if I were to calculate this area, then this area right here is found by taking the y value, 1/2, the y value of the curve, it's like a triangle, times the base. The y value of the curve is a rate. and a rate times your x-axis units, which would be your distance units. So if I take a distance unit times a rate unit, which is distance over time, x is time. I wasn't prepared for this. I wasn't thinking this was coming. Here you go, time. So if I take time times distance over time, you get distance traveled. So this is going to have a lot to do with this idea of how do I reconstruct the original function. I use the rate to figure out how far I have traveled. And you do it by calculating these areas. And the fact that this is a negative area because it's below means that losing quantity. So I start with a quantity of 0 and then I figure out how much I've lost. Well, this is a little bit more than 2, say 2.2. Half of 2.2 would be 1.1 times 1. So it's about 1.1. So in this section, we've lost about 1.1 of our quantity. So that's going to give me a point here. Likewise, coming up here, same thing. Now I'm gaining area. I'm accumulating because my rate's positive. So I'm currently down here at 1.1. How much did I add using my rate? Well, this is at about, say, 1.6. Half of 1.6 is going to be 0.8 times 1 would be 0.8. So I gain 0.8 back. So I'm going to come back up 0.8 from where I am at 1.1. So that puts me at about here. Notice that now, of course, this is not a constant rate, so there's some curvature to this coming up. Now I'm going to look at this next section right here, and we're estimating right here. This is called the eyeball method of coming back. This area right here is definitely, I'm adding another 1 by 1 square, and let's say that's about a half a square. So I'm adding about 1.5 back to where I currently am. So let's go up another 1.5. So yeah, at least 1.5. So now we're about here. Okay, I might come adjust my curve a little bit here. I'm just putting some important points on. And then in this section, I'm still accumulating from where I currently am. So I accumulate at least another 1.5. Okay, so we go up another 1-ish and a half. So now I'm there. Okay, start adding that in. And then I'm accumulating a little bit more here. This whole section. So that's accumulating 1, 2.5 squares. So I have to go up another 1, 2.5. So maybe we're about right there. Okay, I'm going to fix concavity and stuff in a second. And then still accumulating. I'm going to have to go even higher than where I am. So let's say I've accumulated, probably this is a little bit less than 1. That's maybe 3/4. So maybe 0.9, 0.7, 1.6, plus this little section. Or you could treat this like a triangle with a height of 3 by 1. And so 1/2, 3 by 1 is 1.5. So I got to go another 1.5 up for this accumulation. So now we're up here. And then once I get to here, I start losing. I'm not accumulating anymore because I have a negative rate. So I'd say that's about 1-ish back down. And then we're still losing. Okay. So the rate's negative. So I'm still from where I am going down because my rate is negative. So I'm going down about, what is this, 1.5, let's say 1.4 divided by 2, 0.7-ish, because that's a triangle. So I come down about 0.7-ish, and then all of a sudden now I'm accumulating again. So now I'm getting larger, and so now I'm going back up about 2.4, so about 2.2 back up, 2.2 back up to there. All right, so let's kind of smooth this out, and then let's kind of think about what our function characteristics were. We said that there were extrema, relative min at 1 and 8, Oops, it would be helpful if I actually went over to 8 before I went back up. So at 1 and 8, and a relative max at 6, check, we've got that in. We said that it was increasing from 1 to 6, 1 to 6, so it's increasing this entire time, and from 8 to 9, and then it was decreasing 0 to 1, so we've got that in, so check on that. And now let's get our concavity right, which is below. We said it was concave up for 0 to 2. I'm good there, concave up. And then it had to switch, so 2 to 3, it's down. So I'm going to exaggerate this now down, and maybe erase this part right here, because now I'm getting my concavity in there. And then from 3 to 5, it's concave up. So on this whole section right here, let's make sure we make it concave up. Okay. And then from 5 to 7, it's down. So 5 until 7. Oh, you know what? I'm trying to figure out what I think I did here. Because from here, I went down about half of 1.4. There should be a point here where it's going to switch. And then from 7 to 9, it's concave up. So there we go. And there we go. We have reconstructed our graph. Now, of course, we are using this fact that our x value times our rate is going to give us our accumulation. And if the rate is positive, we add to where we were previously. And if the rate is negative, we subtract from where we were previously. So this is a preview of chapter 5. What we're going to use the antiderivative for, the working backwards version. But we can get a close estimate of what we are at. Right? And then, if possible, determine the x values at which f attains its max or min values. Well, in that case, we're on the closed interval, so g, going back to a review of 4.1, is EVT. G, EVT. We had a continuous differentiable function, and it was continuous on the closed interval from 0 to 9. Therefore, we were able to do EVT. So we need to check our endpoints, 0 and 9, and then we need to check all the relative extrema, which we're at 1. Let me just make my chart over here so I have more room. X, Y. So 0, 9, and then we had relative extrema at 1, at 6, and 8. So, and then by the EVT, we're calculating our y values. Now, we're going to do this because we estimated our y values over here. So, we had said at 1, it's about negative 1.1. At 0, it was 0. At 6, we were approximately, let's see, from here, what did I say I went up? A little bit more than 2. So I was at 3, 4, 5-ish, and I went up 2 more. I'm at 7 point something. Okay. 7.2-ish, right? We're estimating. And then we had our 8, where we went back down again. So, and how much did we go back down, we said? From here, actually here all the way to there, if I think of this as a triangle, just to kind of get a good estimate, it's 2 wide and maybe 1.5 tall. So half of 2 is 1 times, so that's about 1.5 down from where we were. So 1.5 from that would be 5.7-ish. Okay. And then for 9, from there we went back up, and what did I estimate we had there? 1 by 2.2. So about 1.1 back up. So add 1.1 to that, so that's about 6.8-ish. Can we determine our absolute max and min? Well, sure, because the idea is looking at the areas. Even though I don't know exactly what these values are, I definitely know that at 1, well, it's not going to be at 0, okay, because we went down from 0. The most obvious one is this. This is going to be our absolute min of negative 1.1-ish at x equal to 1. That's definitely your absolute min. And then your absolute max, when we were calculating these areas to help build my curve, I was good all the way up to here, and I just wanted to make sure, that's why I looked at these values of these two parts, that how much I came down, was it more or less than how much I came up? And what you realize is that when I looked at the area, I went down a whole bunch and not up as much, so that has to be my absolute max of around 7.2-ish at x equal to 6. All right. So that is giving us an estimate. And so the location, and it just said the x values, it didn't really have to know what the y values were. The lowest value occurs at x equal to 1, and the highest value is going to occur at x equal to 6, simply by this investigation. And we'll do more with that in Chapter 5. All right, now I'm going to leave this second one, part of Example 5, for you to do. And I'm also going to come down here, and I'm going to leave this Example 6 as something for you to do. This is a kind of section 4.6 idea. And because 4.1, 4.2, 4.3, 4.4, and 4.6 are so interrelated, you actually have all the skills that you need in order to sketch the graph of these functions. You can use your knowledge from pre-calculus. You can use your knowledge about finding absolute extrema to find your maxes and mins if you have closed intervals. You can use your first derivative test and your increasing-decreasing test to determine where the function is increasing or decreasing. You can use your second derivative to do the concavity test to determine in concave up and concave down. We've talked a lot about determining discontinuities, cusp, and vertical tangents, and points of inflection. So I want you to put it all together and see if you can, for these 3 examples, come up with what you think the graph looks like. And then that will finish out our 4.4 notes for discussion next class.